The next module of this talk is the texture of metamorphic rocks. Texture is a term that describes the size, shape and orientation of the grains constituting a rock, as well as the relationship between these grains. Metamorphic textures can be grouped into three main groups. Number 1, relict texture. It is also called as palimpsest textures. These are textures inherited from the original rock type and which have survived metamorphism. Number 2, typomorphic textures. Typomorphic textures are characteristics of metamorphism. And number 3 is the superimposed textures. These textures are characteristics of a post-metamorphic event, for example, alteration, weathering, etc. Other smaller groups as reaction textures, polydeformational textures, etc. may also be typomorphic or replacement, but are grouped separately because they have some genetic connotation. Now, let us discuss these textures one by one. Relict textures. There are several types of relict textures. Relict textures in metamorphic rocks are indicated by applying the prefix blasto to the original textural name. Relict textures are best preserved in low grade rocks. Examples of such textures include porphyritic, ophitic, intergranular, amygdaloidal, spherulitic, variolitic, piezolitic and oolitic. Next, B. Typomorphic textures. Textures of typomorphic type are characteristics of thermal metamorphism. When thermal metamorphism is not associated with any deformation, the mineral grains are randomly oriented, resulting in either granoblastic or hornfelsic textures. Please note that the granoblastic texture can also develop in regionally metamorphosed rocks. The following are some of the types of granoblastic textures. Number 1, granoblastic polygonal, where the equidimensional grains may have well developed crystal faces resulting in straight grain boundaries and where triple junctions are common. Number 2, granoblastic interlobate, where the grain boundaries are somewhat irregular. Number 3, granoblastic amoeboid, where all the grains have irregular outlines and all the minerals are anhedral. Number 4, granoblastic decussate, where the interlocking randomly oriented crystals are somewhat elongate, prismatic or subvideoblastic, usually applied to rocks with one or two mineral species only. Triple junctions are common. Number 5, nodular, results from the growth of oval shaped porphyroblasts of such minerals as cordierite or scapolite in association with other randomly oriented minerals as quartz, etc. Textures of dynamic metamorphism. This includes textures like porphyroclastic texture. It is a texture produced by the crushing or fragmentation of large grains, resulting in two distinct grain size distribution of the same mineral, coarser grained porphyroclasts and the finer grained fragments. Next, mortar texture. This is similar to porphyroclastic, but in which the smaller fragments are further crushed to finer and finer sizes, close to becoming powders, while some porphyroclasts still persist. Next type of texture is protomyelinitic, a more advanced stage of cataclasis where some minerals begin to deform in a ductile manner, giving rise to an incipient foliation or preferred orientation. Orthomyelinitic or myelinitic texture, where the rocks develop a well defined foliation in quartz rich rocks. An orthomyelinitic fabric is often indicated by quartz crystals elongated like ribbons or flames, that is ribbon quartz. Next, polygonized or recrystallized or annealed or ultramyelinitic texture. The most advanced stages of cataclastic metamorphism result in the recrystallization of the highly strained crystals into smaller ones, developing a granoblastic polygonal texture. At the same time, a foliation defined by micaceous or prismatic mineral persists. Next, crystallization textures, that means the textures that are produced due to the factor of crystallization. They are porphyroblastic texture, where coarse grained metamorphic minerals, that is porphyroblasts, occur in a matrix of finer grained crystals. Poikiloblastic texture, where coarse grained metamorphic minerals contain numerous inclusions of finer grained crystals of other minerals. It is of different types. One, fishnet or skeletal texture indicates rapid crystallization. Sieve texture, then rotational texture, where the inclusions are oriented at an angle that suggests that the poikiloblast may have rotated during its growth, thus indicating syndeformational or syntectonic growth. An alternative interpretation of such texture is the rotation of the foliation during the growth of the poikiloblast, which still makes the growth syndeformational. Snowball texture, similar to rotational texture, but where the inclusions define a spiral shaped trail which may have developed from the rolling over of the poikiloblasts. Helicitic texture, where the poikiloblasts overgrow the pre-existing foliation. This texture therefore indicates post-tectonic crystallization of the poikiloblasts. Replacement textures, or it is also called as superimposed textures. Mesh texture develops in serpentinites, where the needle shaped serpentine minerals occur in aggregates interwoven like a mesh. Hourglass texture, also in serpentinites, where the serpentine minerals replace the granular olivine crystals, giving rise to hourglass like appearances. Bastite texture, a third texture that occurs in serpentinites, where orthopyroxene crystals were completely replaced by aggregate of serpentine minerals, retaining the prismatic shape of the original orthopyroxenes. Pseudomorphic replacement textures. This includes single crystal, multi-crystal, multi-phase or multi-crystal textures. Next is reaction textures. Under the reaction textures, several types of textures develop, that is epitaxial overgrowth. Epitaxial overgrowth is characterized by optical continuity between the mineral and its overgrowth. Both the mineral and the overgrowth must belong to the same structural group and may possibly be the same mineral. This type of overgrowth is controlled fully by the matrix mineral. Topotactic replacement. One mineral overgrows another of a similar structure. For example, actinolite rims on glaucophane. Orientation of overgrowing mineral is controlled by that of the overgrown one. Caliphatic texture. It is also a replacement texture. A caliphatic texture is a replacement of one mineral along its rim by an intergrowth of two or more minerals in a way that the new minerals almost completely surround the mineral being replaced. The term is most commonly used when the replacing minerals form during retrogression. Examples include caliphatic rims of chlorite plus iron oxides after garnet. Reaction rim texture, when one mineral replaces along another its rims, suggesting a reaction between both the phases. The contacts between both the phases are irregular. Corona texture, several concentric layers of one or more minerals completely encircling an older phase. The layers, which range from 1 to 5 in number, represent a sequence of reactions that have taken place to replace the mineral in the core or center of the corona. Coronas form during both prograde or retrograde metamorphism. Atoll texture, where the core of a mineral is dissolved or replaced, leaving behind a surviving rim. Such textures usually form due to an original compositional zoning within the mineral with the replaced core. Intergrowth texture. This includes texture like symplectites. It is also a kind of reaction texture. Symplectites are irregular fine-grained mineral intergrowths that form as a result of a certain reaction that did not go to completion. These intergrowths are often recognized by their wormy appearance and often occur along the boundaries of reacting minerals. Next type is the polydeformational or polymetamorphic textures, crenulated cleavages and or schistosity. This results from the folding of a foliation. SC fabric, a more advanced stage of crenulation where one or more minerals are oriented along the crenulated surface to define a new foliation S2 at an angle to the older foliation S1. This commonly involves some form of recrystallization. The next module of this lecture is the classification of the metamorphic rocks. Classification of metamorphic rocks depends on what is visible in the rock and its degree of metamorphism. Note that classification is generally loose and practical such that names can be adopted to describe the rock in the most satisfactory way that conveys the important characteristics. Three kinds of criteria are normally employed. They are: number 1, mineralogical criteria; number 2, chemical; number 3, protolithic. In addition to these conventions, certain non-foliated rocks with specific chemical compositions and or mineral assemblages are given specific names. These are as follows: amphibolites. These are medium to coarse grained dark colored rocks whose principal minerals are hornblende and plagioclase. They result from metamorphism of basic igneous rocks. Foliation is highly variable, but when present, the term schist can be appended to the name, that is amphibolite schist. Marbles. These are rocks composed mostly of calcite and less commonly of dolomite. They result from metamorphism of limestones and dolostones. Some foliation may be present if the marble contains micas. Eclogites. These are medium to coarse grained, consisting mostly of garnet and green clinopyroxene called womphosite, that result from high grade metamorphism of basic igneous rocks. Eclogites usually do not show foliation. Quartzites, quartz arenites and chert both are composed mostly of SiO2. Since quartz is stable over a wide range of pressures and temperatures, metamorphism of quartz arenites and cherts will result only in the recrystallization of quartz, forming a hard rock with interlocking crystals of quartz. Such a rock is called a quartzite. Serpentinites. Serpentinites are rocks that consist mostly of serpentine. These form by hydrothermal metamorphism of ultra basic igneous rocks. Soapstones. Soapstones are rocks that contain an abundance of talc, which gives the rock a greasy feel similar to that of soap. Talc is an Mg rich mineral, and thus soapstones from ultra basic igneous protoliths like peridotite, donaites and pyroxenites, usually by hydrothermal alteration. Skarns. Skarns are rocks that originate from contact metamorphism of limestones or dolestones and show evidence of having exchanged constituents with the intruding magma. Mylonites. Mylonites are cataclysmic metamorphic rocks that are produced along shear zones deep in the crust. They are usually fine grained, sometimes glassy, that are streaky or layered, with the layers and streaks having been drawn out by ductile shear. So, coming to the last part of this lecture, conclusions. Metamorphic rocks constitute a very important part of the study of the different types of rocks. The study of metamorphic rocks in all its variety enables one to trace the evolution of the earth's crust right from its primitive stage up to the present. The chemistry of the metamorphosed sedimentary rocks reveals their parentage. The mineral assemblage of metamorphic rocks present a fossilized record of the pressure temperature regimes that prevailed in different parts of the crust at different times in the past.